Now we're going to move on to another important quantity in astronomy, which is escape velocity. So we learned in the last lecture how to get the surface gravity of an object. So we want to compare what the surface gravity looks like to how hard it is to get out of the gravitational pull of that object. And that comes from the escape velocity. So the escape velocity is given by the square root of 2 times the Newton's gravitational constant times the mass divided by the radius. And everything is under the square root. So we're going to use this and look at how we use these big numbers to calculate the escape velocity of the Earth and the Moon and compare them. From our previous problem, we knew that the g of the Earth was much greater than g of the Moon, which causes us to feel almost weightless if we were to walk on the Moon. So how does that compare to escape velocities? So g is our 6.67 times 10 to the minus 11 meters cubed per kilogram second squared. So let's start with Earth. It has the mass of 6.0 times 10 to the 24 kilograms. And it has a radius of 6.4 times 10 to the 6 meters. So the escape velocity is the square root of 2 times g, 6.67 times 10 to the minus 11, times m, 6.0 times 10 to the 24, divided by r, 6.4 times 10 to the 6. And this square root covers everything. So we have to use our same methodology we used in the surface gravity and look at prefixes first and then look at exponents. So we have a 2, a 6.67, a 6, and a 6.4. And all of that is under the square root. So our prefixes are 2 times 6.67 times 6.0 over 6.4. So our numerator here, 2 times 6.67 times 6. That's 80.04. And that's divided by our denominator, which is 6.4. If you do our division, we get 12.51. Rounding, of course. So this is our numerator, but it's under the square root. So we have to take the square root of this guy. So square root of this is the square root of 12.51, and that is 3.54 with a little bit of rounding. So we do the square root operator normally on the prefix, but it'll be different when we look at the exponents. So let's look at those next. The 2 has no exponent. We have negative 11, 24, and 6. So our exponents have negative 11 plus 24 over 6. So using the same math we did before, you add the exponents when they're multiplied. So 24 minus 11 is 13, and that's divided by 6. So when you subtract exponents when they're divided. So that is 7. So our exponent under the square root is 7. But it's square rooted. So when we did a square of a exponent, we multiplied it by 2. When you take a square root, it's the opposite of squaring it. So you divide this by 2. So this is 4.5. So our final exponent is 4.5. So when we come down here, 10 to the 4.5. This is from our exponents. And then let's look at our units. So G has meters cubed, kilograms per second squared. If you multiply that by a mass, the mass is in kilograms, and you divide it by a radius, that's a meter. The kilograms of the units cancel. 1 meter will cancel with 1 up here and give you a meters squared. So if the multiplication yields meters squared per second squared. Cool. Then you take the square root. Square root of a meter squared is a meter, and the square root of a second squared is a second. So our final units for escape velocity is meters per second. So our final escape velocity looks like this. 3.54 times 10 to the 4.5 meters per second for Earth. So now we have to repeat that process, or let's go over what we did. Our escape velocity is given by this equation with the square root, found by Isaac Newton. We know that the gravitational pull of Earth is stronger than the moon from our previous problem. We have our Newton's gravitational constant, and when we multiply everything out, we know that our final escape velocity will have meters per second as our unit. We're given the radius and mass of the Earth from our table. We plug them in to our escape velocity equation. We do our prefixes, which is 2, 6.67, 6, and 6.4. When you do all that math out, you get 12.51, but all of that is under a square root, so you do math normally under on prefixes, so you get the square root of 12.51, which is 3.54. Next, you look at the exponents. So we have negative 11, 24, and 6, which gives us 13 divided by 6, which is 7. When you subtract exponents when you divide. And then in order to account for the square root, you have to divide it by 2, which gave us a 4.5 exponent here. So let's do one more example. Let's look at the moon. The radius of the moon is 6.4 times 10 to the 6 meters. The mass of the moon, oops, sorry, that is not right. Let's go back. The mass of the moon is 7.3 times 10 to the 22 kilograms, same as the last problem. The radius of the moon is 1.7 times 10 to the 6 meters. So the escape velocity is the square root of 2 times g, 6.67 times 10 to the minus 11, times m, 7.3 times 10 to the 22, divided by r, 1.7 times 10 to the 6. So we're going to do our prefixes, 2, 6.67, 7.3, and 1.7. 2 times 6.67 times 7.3 divided by 1.7. 2 times 6.67 times 7.3. Our numerator is 97.382, and our denominator is 1.7. If we do that division, we get 57.28. And then we have to take the square root because all of this stuff is under the square root. So if we take the square root of our whole value, we get our final prefix to be 7.57. Our prefixes are in blue, so that is our final prefix. Next, we have to do our exponents. Negative 11, 22, and 6. So, negative 11, you add when you multiply things with exponents, and you divide, or you subtract when you divide. So our numerator is 22 minus 11, 11. And our denominator is 6. So you subtract, that gives you 5. When you take the square root, you have to divide your exponent by 2. So 5 halves is our exponent, which is 2.5. So our final answer is this times 10 to the 2.5 from our exponents, and then meters per second from our units. So this number, since its exponent is smaller, is much smaller than the answer we got for Earth. So it requires you to have a much smaller velocity to leave the gravitational pull of the moon because its surface gravity is smaller.